Log on, tune in, find out. Another good idea from Cambridge.
So for the invitation and this opportunity to present this talk. Now, so this talk is about fixed parameter tractability and kernelization, and how certain basic things in discrete harmonic analysis, probabilistic method, and linear algebra can be used there to get some interesting results. Now, so it's 4 parts. Introduction, where I will try to explain what is fixed parameter tractability and kernelization. A very short introduction to parameterized complexity and algorithms. Then I will show you how to use simple tools and of probabilistic method and harmonic analysis for one of important problems in the area. Then the same thing for linear algebra, and then I will go through certain other problems, just a selection of other problems for which these methods can be used. Okay, let's start from introduction. So what is a parameterized problem? So it's a set of pairs where x is the main part and k, which is usually an integer, is called the parameter. And in many applications, in most applications, k is much smaller than the size of x. Just to give you an example, k vertex cover. So here we are given a graph, and we want to and we need to decide if there is a subset of the vertex set such that every edge has a vertex in that subset. Namely, that subset of vertices covers all edges, and we want to find such a subset. We want to decide if there is such a subset of cardinality at most k. So we are only interested in vertex covered of cardinality at most k.
So the x here is the graph, right?
Yeah. So G is a graph, and we want just to decide whether there is a small set of vertices which covers every edge, and so small means that the size of that set is at most k. Now, so the second example is k-independent set. So again, here we are given a graph, and we want to decide if there is an independent set of size at most k. Right?
Size.
So size meaning the number of vertices.
At least k.
Oh yes, at least k, sorry, at least k. Yes, at least k, just copy it from the other one. So then another one is the one which will be prominent today. So k max lin above average. So here we are given a system of linear equations over f2, and so in each equation has a positive integral weight, and we want to decide if there is an assignment of values to the variables y such that the total weight of the satisfied equation is at least k plus the half of the total weight of all equations. Obviously, we can always satisfy at least half because of the expectations, say, and argument, and of course it's very easy in this case to de-randomize this. So, but we want not just half, we want more than half by at least k.
So you say it's very easy to de-randomize the selection?
I mean, they randomize half. If you want half of the weights, you can easily get it either by directly de-randomizing this argument or using Gaussian kind of elimination argument. So it's not difficult to do this one. But we want not just half, we want more than that. Okay. Now, what is when a parameterized problem is called fixed parameter tractable? When when we can solve this problem in this time, f of k, any function of k, but just k, times the size of the instance in a constant degree. So basically what we want to say is that if subject to k, if you fix k, then you get a polynomial time algorithm. But of course, if our problem, like the problems we consider here, is NP-hard, so you cannot expect a polynomial time algorithm. But at least what you want, if you want to to put the complexity of the problem in k. Basically, you hide it in the parameter k. And since parameter k is small, at least you want it to be small in your applications, then this time the total running time is not that big. So the problem becomes feasible, you can solve it. Now, one example is as follows. So say running time, you have running time 2 to the power of k times the size of the problem. And this function is much smaller, often much smaller than the other one, say the size of the problem to the power of k. Now, for example, if you take the size of the problem 1000 and k equal 10, then t1 is less than 1 second on a modern computer, while t2 isn't feasible, basically. You cannot solve it at all. And so, and therefore, this example tells you that it's really desirable to create algorithms which run in time f of k times a polynomial. And and there are several such problems. For example, k vertex cover is fixed parameter tractable, and there is a fast algorithm for that problem, such that, say, up to k equal 400 with quite large n, we can solve that problem. And it is indeed this kind of algorithms, they are used indeed in applications already. Now, say, on the other hand, k-independent set is W1 hard. I'm not going to explain what W1 hard means, but this is kind of analog of NP hardness, classical NP hardness for this type of problems. And like we believe that P is not equal to NP, people working in parameterized complexity widely believe that FPT, this class of problems solved in which are fixed parameter tractable, are not, this class is not equal to W1, and therefore we believe that this problem is not fixed parameter tractable. Now let's move to this k max lean above average.
So when you say highly unlikely, I mean, is the view that the distinction here is as unlikely as P equals NP?
No, it is weaker. It is weaker than that, but
because I mean, no one would say it's highly unlikely that P equals NP. They'd say obviously it's wrong.
Well, there is no mathematical proof of that, so we cannot say just it's not equal. I would say yes, it's very unlikely, extremely unlikely if you want that they are not equal. Here, I would not be that strong, but it's also almost the same strength here, I think.
Is
yeah.
there a completeness thing here too? That there's a class of problems where they reduce to each other?
Yes, exactly. Yes, and there is class W2 and so on and so forth. And in this case, fortunately or unfortunately, there are many classes like that. But since we are going to speak here mainly on the positive outcomes, namely the problems are fixed parameter tractable, I'm not going to go too much into this one. Now, so Mahajan, Raman, and Sigdar asked what is the complexity of K max lean above average. So half of the weights of all equations plus K. Can we decide that or not? If there is any assignment to the variables of that system over F2 where we can satisfy half weight plus K. Now, another notion related to FPT is kernelization. So kernelization is basically a polynomial time algorithm that maps an instance of parameterized problem to another instance, which we call the kernel. such that, you know, they are equivalent. Yes, if and only if yes. We are speaking about the decision problem here. Now, the second condition is very important. The second condition says that k, the parameter k prime, the parameter in the second instance, must be bounded by a function of k, and moreover, the size of that second instance is also bounded by a function of k. So we want really to reduce it such that the size, even the size of the problem, is bounded by some function of k. So, and in this case, we call g of k is called the size of the kernel. And for example, for a k vertex cover, there is a kernel with at most 2 k vertices, a k square edges, and so the size of that kernel is m plus n, k squared plus 2k. So it's a quadratic kernel here.
So is that because the point with k vertex cover is that if you've got too many edges, you obviously can't do it?
Yeah. It's also to do with degrees. If it's large degrees, you cannot do it, and so on and so forth. Yeah. Because you care only about vertex covers of size at most, of cardinality at most k. That's all you care.
2k edges, you're screwed.
Yeah. Yes. Yeah. Now, so what is interesting but not difficult to prove is that a decidable parameterized problem is fixed parameter tractable if and only if it admits kernelization. And so we believe, therefore, that k-independent set has no kernel. Yeah. Now, what is interesting is to get polynomial size kernels for preprocessing, because kernelization is basically a preprocessing. You are given a decision problem. You want to reduce the size of your instance, and without losing kind of your parameter on the way. And of course, to be of kind of practical interest, you want this to be the size to be bounded by a low degree polynomial. Now, so unfortunately, many fixed parameter tractable problems do not have polynomial size kernels unless we have another condition, co-NP is part of NP poly, and that's another complexity assumption, which again widely believed not to be true. And now what we know is that, again, I repeat that from what we know now is that k vertex cover has a polynomial size kernel because it's fixed parameter tractable. Now, so we can reformulate that open question of Mahajan, Raman, and Sigdar, is there any kernel for this k max lin above average? So you can ask whether it's fixed parameter tractable or it has a kernel. It's the same question. Just wanted to illustrate that these two things are equivalent. And since I'm going to speak here about kernels, not really about complexity of algorithms, because I think it's easier to speak and a bit more mathematical, because we can forget about algorithms mostly, okay, in this case. And the audience is mostly mathematicians, so I think it suits fine to everyone. Now, so in this area, we normally consider reduction rules first. So you are given a problem, so you're given an instance of a problem. You apply certain reduction rules such that they reduce this instance to an equivalent instance, but probably a bit smaller size. So first reduction rule is obvious. So you reduce the system such that no two equations have the same set of variables. If the left-hand sides are equivalent to equations, obviously you can put them into one, depending on the right-hand side, and of course you need to adjust the weights, but it's clear what to do in this case. Now, second rule is a bit less obvious.
So when you say the same set of variables, you mean because you're over F2, you look at the ones that have coefficient 1?
Yeah, that's the coefficients 1. Say if it's x1 plus x2 equal 1 of weight 2, and x1 plus x2 equals 0 with weight 1. So you replace everything by x1 plus x2 equal what, 1 with weight 1, right? Now, so rule 2. Here what you do, you look at the matrix of the system, the main matrix of the system. And so what you can do is you can assume that the rank of the matrix is m, the number of variables, because if it's larger than that, you can eliminate certain variables. And this is an important observation, because we want to know that always n is less or equal than m. That's what we want to know, because if we bound, say, m, then at the same time we can bound n from above. And so when we apply rule 1 as long as possible, and then rule 2 as long as possible, then what we get in the end we call an irreducible system, such that no further reductions are possible. Even rule 1, easy to see that even rule 1 is not anymore applicable here. So, and we are going to deal mainly with these irreducible systems. Now, so then also we want to view this problem, Max-Lin above average, in two more forms. There's equivalent forms, but in different settings it's easier to look at that problem from different angles. So product form, so in this case you basically, instead of F2, you consider domain minus 1, 1, and instead of sums you consider products. And so that's what's written there. So you replace sums by products and 1 by 0, 0 by 1, and 1 by minus 1. Now also you can write it in the function form. So in this case you simply sum up all this, you take the sum over all equation. The j is an index of the equation, and then times dj, where dj is the product of cj, the right hand side of this product form equation, times the weight of the equation, and times the product, the usual product, which we consider in Fourier analysis. And so it's easy to see that the answer to k Max-Lin above average is yes, if and only if the maximum of that function is more equal than 2k. So if we want to study that problem, we can study that problem also as a problem of maximization of this type of functions. Well, the only thing is that we assume that the first coefficient in Fourier expansion is 0. I mean, free coefficient is 0 because we don't have any empty equations here. Okay. So basically, in the paper which I already mentioned by Mahajan and others, there were several. That was a survey paper, and there were several problems, a dozen of problems, open problems of above average or above expectation, or in general above a tight lower bound. And so, and it turned out that you can solve many of those problems, but then you need to use not just combinatorial approaches. And so one simple method which we suggested to solve several of those problems is what we call strictly above below expectation method. So what we do, we look at a parameterized problem with parameter k, then we apply some reduction rules depending on the problem. Then we introduce some random variables with expectation equals 0, and such that the probability, if the probability of that random variable to be more equal than k is positive, then the answer to the problem is yes. Just in one direction is enough in many cases. Now, so suppose we introduce such a random variable. Then if x is symmetric sometimes, then okay, then we can use a simple inequality that probability of x more equal than square root of the second moment is always positive, and so now if this is indeed symmetric, then it's very easy. So square root of this second moment is more equal than k, then the answer is yes, we know from the condition for x. And now if it's not, then a problem-specific analysis can also give us something, and you will see that it works sometimes. Now, most of the time, unfortunately, these random variables are not symmetric. And so in this case, you need to do something a bit more elaborated. And so in these cases, we use this inequality by Alon and others. So what you get is that if the first moment is 0, second moment is positive, and then we have kind of hyper contractive inequality, then again we can see that x goes beyond sigma over 2 square of b, with positive probability. And so the question is how to check this hypercontractive inequality, of course using hypercontractive inequality, because that's what you expect to do. And I think in this audience I don't need to speak too much about this one. So we use this 4-2 case, which is often used in theoretical computer science nowadays. And right, so basically we can use hypercontractive inequality, and we do use hypercontractive inequality in such cases. Now, also because of that Max-Lin above average, we got another formulation of hypercontractive inequality. So as you can see here, with somewhat smaller coefficients. So what is rho? Rho is the maximum number of appearances of a number I in I. So which means that it's the maximum number of appearances of a variable in terms of this Fourier expansion, right? So this is rho, and then you, instead of the degree of function, you can use rho actually as the coefficient in hypercontractive inequality. Here I wrote case 4-2 case. Actually, this can be generalized to yeah.
No, I'm just
Yeah. So, but not here. We know at least that the coefficient is optimal. We don't know an optimal coefficient in the general case. This coefficient is optimal because even if you take this simple function f of x equal 1 plus the sum of xi's, then you will get that in this inequality you have equality. So okay, so now let's use this method. So for example, so to use this method is we consider our problem in the function form. So namely, we are given a function, what I call pseudo-Boolean function. Pseudo-Boolean function is the one we maps -1, 1 to the power of n to the set of reals. So if you get this pseudo-Boolean function, and suppose that there is some set u such that the variables whose indices belongs to u, this number, those variables are odd number in every equation. So, or in a particular case, if every equation has an odd number of variables, okay. In this case, we can solve that problem. So, because in this case, f is a symmetric random variable. It's easy to check. And so then the second moment is no problem by Parseval. Then by that simple inequality, we get that the probability of f more equal than square root of n is positive. now is square root of m is more equal than k, then the answer to our problem is yes. Otherwise, we get a bound on m, a quadratic bound on m, and therefore a quadratic bound on n, and that means we got a polynomial size kernel. So this case is simple. Okay. So the next one is consider the case when in every equation we have at most variables. Okay, in this case we can use the classic hypercontractive inequality and that inequality of alone, and then we get again a quadratic kernel. Now, of course, we can also make use of that dual hypercontractive inequality, which uses rho, the maximum number of appearances of a variable. Well, in that case, when we can use it? Well, if no variable appears in more than row equations. Okay, so we can use that, and you see why we call it dual, in a sense that we have duality here. Of course, not necessarily this r or rho must be constants. You can relax this as well, but even if you relax that, you cannot solve the whole thing. You cannot solve the problem. You cannot check whether our problem k max ln above average is fixed parameter tractable or not. So even though we can extend a bit what I presented to you, we cannot get the general case, and we actually will fall far short from this. And still an open now, even though I'm going to show you that the problem is fixed parameter tractable using a different approach, still there is an open question. Does this problem admit a polynomial size kernel? So I'm going to show to you that there is a kernel here, but to this day we don't know whether there is a polynomial size kernel, because here, using this probabilistic approach, we could show that there is a polynomial size kernel, but only in some special cases, not in general case. Now, okay, let's look at another approach. So it comes from linear algebra. So this is a joint paper with Jones, Mark Jones is here, my PhD student, and also with Imre Ruja. Probably some of you know him. Yeah, okay. So it's an unusual setting for him, I guess. Okay, so again, let's consider the product form, and then let's consider the following algorithm, which we call H. So we do basically Gaussian elimination. We choose, as long as our system is non-empty, we choose an arbitrary equation, mark an arbitrary variable in that equation, then mark that equation and delete it from the system. Now we replace, then we do Gaussian elimination. So we take every remaining equation where we have that variable, marked variable, and eliminate that equation from the eliminate that variable from that equation. And so this is in a product form, but you can easily imagine what is going to happen in the usual additive form. Then we apply reduction rule to the system, and you continue. The problem here is that you may run out of equations very soon. So it's not like you are going to go for many steps in general, so you may run out of equations very soon, which is bad, because we would like to run out of equation and not so soon, because of the following simple lemma. If we have an irreducible system, and if we assume that algorithm H marks equation of total weight W, then if W is more or equal than K, then the answer to our problem is yes. So we want to run that algorithm for as much as we can. I mean, to produce the largest, the weight of marked equation to be as large as possible. So
the point of this reduction is that you're producing a system in which certain variables only appear in one equation. Is that the idea?
No, the idea is like with Gaussian elimination. You take an equation, you take a variable there, you eliminate that variable from the rest of equations.
Yeah.
Okay, you mark that equation and just
So
delete it from the set. Then you continue.
So the point is you can solve that equation at the end just by substituting a value for that vector.
Yes, yes, exactly.
So
because
so having marked an equation, you've then got the others which you've eliminated, and you just
Yes.
pick another one
yes,
and mark a variable.
yeah,
in that instead.
that's right.
And
So it's basically equivalent to an assumption that you say yes, this variable will be satisfied. That equation, sorry, will be satisfied. Yeah. So you make this bold assumption that the equation will be satisfied, and then you continue. Of course.
So when you run out of equations, you run out because what?
You run out of equations because you see if you have in the middle you have an equation x1 plus x2 equal 1 and x1 plus x2 equals 0 with equal weights, then they cancel each other, right? And this cancellation does not change the average. That does not change not the average. It does not change an excess above the average, right? So therefore, we get rid of these pairs without any problem because we do not change the excess. This k or whatever you call it, the excess is not changed. And so you don't want this algorithm to stop too soon. So what to do? So one thing what to do is to consider some free sets. So assume that we have two sets. K is a subset of M, and they are both sets of vectors in F to N. So K is M sum free if no sum of two or more vectors in K is equal to a vector in M. So it's not the usual sum free thing where you consider only pairs. Here you consider any sums as long as they have at least two summands there. Okay? So it's more than just the usual sum free thing. So what we have is this what we call the M sum free lemma, which says that if M is a proper subset of F to N, such that it spans the whole F to N, and and also this zero vector is there. Now, if K is a positive integer and we have that inequality, that M has at least K plus 1 vectors, but at most 2 to the power of N divided by K, then in polynomial time, we can find an M sum free subset K of M, such that the number of vectors there is at least K plus 1. Okay? So we can get, with M being not too big, we can find a relatively large subset K, which is M sum free. Now, that lemma allows us to make a clever choice for marking.
How could the size of M be bigger than K plus 1 help you?
K plus 1. Why not?
I mean, surely if M is smaller, you're better off.
Well, but then you by no way you are going to find K plus 1 vectors in a set which has less than K plus 1 elements. Vectors.
Of M, I'm sorry.
Yeah. Okay. So this is a kind of trivial, condition. Now this lemma is proved using linear algebra. Now, if we use that lemma and the algorithm H, in which we basically look at that system, right? Look at the left-hand side vectors, incidence vectors of the left-hand sides, and then say that this is our set M. Now, we want to then we choose K, which is M sum free. vectors, and those vectors correspond to the equations. Now, if you use those equations for an algorithm H, then you know that it's not difficult to see that all these k+1 equations will survive to the end, which means that you start from the first one and go on, and the system will be non-empty at least by the time you exhausted all of those. And therefore, what we get is that if S is an irreducible system, and if M is more equal than 2k and less or equal than 2 to the power of n divided by 2k minus 1 minus 2, then the answer to our problem is yes. And moreover, we can find this yes assignment to the variables in time, in polynomial time. Now, another theorem which is related to H, to algorithm H, but not related to that M-sum-free lemma, is as follows. It says that there exists actually n to the power of 2k times polynomial time algorithm for the problem. So you see, there is this kind of algorithm, but this algorithm is not fixed parameter tractable. It's not what we want, because 2k, you know, k is in the degree. We want k to be down as a coefficient, not as a degree. Okay, so it's a bad algorithm, but this algorithm will help us to prove also that the problem is fixed parameter tractable. Well, so these two ingredients, these two theorems allows us to do that by combining them together. So this theorem shows that k max ln above average has a kernel, not polynomial kernel, by the way, but a kernel with at most k square log k variables. So here we bound n, the number of variables, not the number of equations. Therefore, we cannot say that the kernel is polynomial. Sometimes, you know, some people get confused and they say, oh, it's a polynomial kernel. No, it's not. Actually, it's not. It's just a number of variables. Now, the proof is simple here. So we simply a simple case analysis. So we know that n is less or equal than m. Now, if m is less than 2k, then we are done. Now, if m is more equal than 2k and less that function in our theorem 1 above, then the answer is yes, we know from that theorem. Now, on the other hand, if m is more equal than 2k, then we can solve the problem in polynomial time. Why? Because we will replace 2n to the power of k in the runtime by m, right? And so we get a polynomial time algorithm. Good. So what's left is these two things, that m is between this exponential function and 2 to the power of 2k minus 1. Well, in this case, is a simple manipulation shows to you that n is basically O of k squared log k. So that's it, basically. Either you can solve the problem and say whether it's yes or no. The answer is yes or no. Or you get a smaller instance of that problem in which the number of variables is at most coefficient time k squared log k.
And then m is at most k to the k or k to the
Yeah. So m could be anything to the power of yeah. Now, on the other hand, using this kernel, we can produce a relatively quick algorithm. I promise not to mention algorithms. I will break my promise here. Okay, so what we can get this algorithm of running time to the power of O and k log k times polynomial. So again, the proof is simple here. We look at an irreducible system with m equations and variables. By previous theorem, in polynomial time, we can either solve the problem for S or get a kernel with at most k squared log k variables. Now, in the last case, because the first case is no interest, we already solved the problem. In the last case, we applied this 2 to the power of 2k times polynomial time algorithm for the problem in where we replace n by its bound in terms of k, and so we get what we want. Okay.
So going back to the previous theorem, assuming that m is a sort of normal sized thing relative to
What
n.
do you mean by normal sized?
Well, say it's n squared at most.
Yeah, then it's polynomial.
Then which of the cases does the job? It's the
M is equal n squared. M is equal n squared. Well, I think it's case 2.
Yeah. Okay, so case 2 is
Yeah.
Case 2 is where the action really happens.
Yes,
Which is
yes.
where the should-
That's right, that's right. Absolutely, absolutely. Theorem 1 is the key here.
Okay, good.
Yeah. Now, let's move on to more applications. Okay, so first of all, let's consider a special case of K max lean above average, which is not absolutely a special case, but anyway, close to a special case. So in this case, every equation has at most r variables, and but we have basically two parameters, or one parameter which is the sum of k and r, right? So so the trend now in parameterized complexity is moved from just one parameter to more parameters, because I guess it will bring more problems to the fold. It will bring more problems to be solvable, and also when the parameters are not that big, because that's important. Now, so let's consider two natural parameters. So here we have a lemma which is similar to the one which we saw before about M some free subsets, but here we assume that we deal with sets M in which all vectors has at most are non-zero coordinates, and then we get that if n is more equal than r times k minus 1 plus 1, then in polynomial time we can find an M some free subset k of M such that k has at least k vectors. Okay, and in this case, this inequality for n more equal than r times k minus 1 plus 1 is sharp, so you cannot improve it here. And this lemma and algorithm H allows us to prove that this kr max r lean above average has a kernel with at most 2k minus 1 times r variables. So it's multilinear in this case, bound for the number of variables. And it also improves a kernel, previously best known kernel of Kim and Ryan Williams, which is quadratic in R, but linear in K. But we still have an open question here. Is there a polynomial size kernel for that problem? Again, if you recall how we proved that if R is bounded from above, then K max lean above average has a polynomial size kernel. Then, because of that hypercontraction inequality, we get basically an exponent in the bound on M because of hypercontractive inequality. So we don't know whether there is a polynomial size kernel for this problem or not.
Is the problem on the bottom right the same as the problem on the top left?
Yes, I forgot to write R there. Yeah, in the middle between max and lean. Yeah. Okay, now let's consider max Assad. So here I just recall that we have a CNF formula with clauses of sizes R1 to Rm and variables y1 to yn. And then we assume that the maximum size of clause is bounded by some constant R. And then we want, so sat f of A is the number of clauses satisfied by an assignment A. And then basically a random assignment, the expectation of the number of satisfied clauses is where is this sum over terms 1 minus 2 to the power of minus I. And so a natural question is whether we can satisfy more than the expected number, more than the average number of clauses. And again, these people, Mahajan and others, they asked about the complexity of that problem. Now, after what you saw, it's probably not difficult to figure out what we are going to do. So, but for simplicity of presentation, I assume that every Ri is just R. And so consider a clause with R variables, then we can assign to that clause a pseudo-Boolean function. And pseudo-Boolean function, and then of course we sum up all the pseudo-Boolean functions for all clauses, and it's not difficult to see that the answer to max R sat above average is yes if and only if that pseudo-Boolean function, the sum, is more equal than k times 2 to the power of R. Okay, and since R is a constant, we are fine with that. You know, it's just a coefficient. Now, so what we do after that, like what we do with many pseudo-Boolean functions, we get a Fourier expansion of it, or we simplify it if you want. That's the other way to look at it. And of course, here the support, you know, is bounded. So by R, and so we can use then this method, probabilistic method, which we looked at before, and get a quadratic kernel. Now, so of course the same approach can be actually extended to constraint satisfaction problems, not necessarily max sat. You can consider any constraint satisfaction problem where you are given n variables and m Boolean formulas such that every formula has at most R variables, and then you define the average number of satisfied formulas, and you want to know whether you can satisfy k more, and yes, you can do it. I mean in fixed parameter tractable time. And yeah, okay. Now, a bit more exciting problem is betweenness. So here we have again set of variables, and then we have set of so-called betweenness constraints, which are of the form vi with j with k, and that such a constraint is satisfied by bijection from the set of variables to 1 to n if this bijection sets vi between vj and vk, right? And so again here we want the betweenness problem, normal betweenness problem, is to find a bijection satisfying the maximum number of constraints. Tight lower bound is m over 3, just 1/3 of all these constraints. Because this is the expected number of satisfied constraints. Now, this problem is difficult. For example, Sherikar and others proved that to approximate betweenness within factor 1 over 3 plus any epsilon is unique games hard.
Does that mean if unique games conjecture is true, then it's hard, or does it mean?
Yes. So now, of course, our natural question here is we want to satisfy m over 3 plus kappa. In this case, we use this kappa as the parameter. And Benny, Shor, asked some time ago, at least it's mentioned in Niedermeyer's book on parameterized complexity and algorithms. What is the parameterized complexity of that problem? And okay, here we use reduction rules. We delete complete triples, which are triples of that form which I wrote there. And after that, of course, once you are done with that, you want to, this is the first step in our approach, then you want to introduce some x required by our method. The problem is that, yes, you can find such x, but anything which we found, there it was difficult to estimate the second moment, and practically impossible to estimate the fourth moment. But we could not use hypercontractive inequality because any x, natural x you construct there, is not polynomial, is not a polynomial of constant bounded degree. So the question is what to do here. Now here we use the following trick with 4 bins. So we look at an instance of this betweenness problem, and then we consider a function which assigns variables, variables actually, into 4 bins. And then we consider phi compatible, this function is called phi. Phi compatible bijection alpha is the one which is compatible with that. So if a variable is put in a smaller bin, then phi is also smaller for that variable. And then what we do, we consider a random phi compatible bijection alpha, and we introduce random variables and also weights, which are also weights. And then it's by linearity of expectation, it's not difficult to see that if the weight of C, if the weight is more equal than kappa, then the answer is to this instance is yes. So it's simply linearity of expectation here. Now, so what it means is that to solve betweenness above average, it's sufficient to find phi for which, the weight is more equal than kappa. So that means that we can forget about alpha. Now, we can forget about bijections from the vertex set to 1 to n, and instead consider only placing these variables into 4 bins. That's all we need. And in this case, it's not difficult to get x, which is of degree 6, then some estimate, which is a bit lengthy in this case, because you cannot use Parseval here, because the x is a polynomial which is not so easy to simplify, analytically. Then you need to use some combinatorics and to prove that it's the second moment is more equal than 11m divided by 768, and the rest is as you saw before. So therefore we know that betweenness above average has a quadratic size kernel, and we proved similar results also for the ternary, for all ternary basically permutation constraint satisfaction problems, but certainly I don't have time to speak about that. Thank you. Yeah.
So you were talking about satisfying systems of linear equations over F2.
Yes.
So if you're working over a different finite field, would your methods extend?
Well, we have not looked at that. I know that this is a natural question, but we didn't have the time to look at that because still there are some exciting problems, and before we start extending or generalizing things, we want to solve those.
But do you have a feeling for whether it would work or not?
I think it should be possible, but I cannot tell you whether it is or not because I didn't try.
Thank you again.
Thank you.